Hello everybody. So we are going to discuss now the next point, which is the difference between the theoretical and excess oxygen and air. And this is something that we discussed before in the beginning of the reactive system part of chapter 4, and it's going to be the same thing. The only difference is that we are making it more specific for combustion reaction. So what we can see here is that or let's go a step back. That if we have a reaction, a combustion reaction that we want to undergo, or let's say we have a fuel that we want to burn, and that we have an option either to go for complete combustion or incomplete combustion. So I'll go back to, I think, one of the slides that we this slide. So let's say we have methane. Let's say we have this fuel, and I'm going to burn methane. So I have, if let's say I have the choice whether to go for the first reaction or the second reaction, which one would I choose? And then we will go to the next point, is how can I make it happen? If I can choose between these two, I would definitely go for the second reaction, which is the complete combustion. And this is for two main reasons. The first is what we started the discussion about combustion reaction with, which is why we do these reactions. What is the main goal of the combustion reactions? And we said that the main goal is to produce heat. And as much as I can, I want to maximize the amount of heat I'm getting from the fuel. So the energy that we get from burning the fuel from completely burning the fuel is higher than the energy we get from the incomplete combustion of the fuel. So it's more economical or more feasible to have a complete combustion reaction, because the amount of heat produced here is higher than the amount of heat produced here. So this is the first thing. The second thing is regarding the emissions or the combustion products that we get from the two reactions. Of course, we know that carbon dioxide is a very it's making a lot of problems to the environment now, and we all know what is going on because of the huge amounts of carbon dioxide that's being released to the atmosphere for burning the fuels in power stations and from the cars and everything, and this is causing the global warming and the change in the weather and everything. But still, it's more or it's less harmful. Let's put it this way: it's less harmful than carbon monoxide. Carbon monoxide is a very, very, very toxic gas, and it can be toxic under very low concentrations. So if carbon dioxide is released with large amounts, it can cause quick death. And also carbon monoxide is non-detectable by the human senses. It doesn't have smell, it doesn't have taste, it doesn't have color, and it's very hard to know that a person is getting toxicity from carbon monoxide. So from the two perspectives, from the energy point of view and from the safety point of view, it's more favorable to go for complete combustion. Now comes the second point, is how can we push the reaction to go for a complete combustion reaction rather than an incomplete combustion reaction. So to answer this question, let's look at this example here. So for this example, we have the complete combustion reaction of pentane. This is a balanced chemical reaction, meaning that all the number of atoms in the left hand side is equal to the number of atoms on the right hand side of each element. And if you look at this reaction, you would see that the stoichiometry of the reaction says that if I, let's say, have 10 moles of pentane, and they will need 80 moles of oxygen to produce 50 moles of carbon dioxide and 60 moles of water vapor. So if you, theoretically speaking, if you provide 80 moles of oxygen for these 10 moles of pentane, we should have complete combustion. This is what we expect. But in reality, what happens is that if the 10 moles of pentane are burned in the presence of just 80 moles of oxygen, what will happen is mostly incomplete combustion. So both will happen, but the incomplete combustion would be very dominant, meaning that it's producing carbon monoxide. And this is something that we should expect. Usually when we burn the fuel, we burn it in presence of nitrogen, because it's we burn with air, it's not with pure oxygen. So nitrogen has very high concentration, it's 4 times the concentration of oxygen. So the partial pressure of oxygen is not very high. Or you can put it in another way, that the possibility of the pentane to find the 1 molecule of pentane to find the 8 molecules of oxygen is not as high as it is if you have or for them to find oxygen to do incomplete combustion. Because for incomplete combustion it will be, and instead of 8 it would be 5.5 moles. So it can find 5.5 moles easier than finding 8 moles. So this is why the incomplete combustion will happen in this case. So in order to push the reaction to be a complete combustion reaction, what we do is we provide more oxygen than needed. So this is what we call the excess oxygen or the excess air. So we provide more oxygen to increase the possibility of the pentane molecule to find the 8 molecules of oxygen. So if I need 80 moles of oxygen, I can provide 100, 120, I can provide 150, I can provide more. And this will increase the chance of the complete combustion reaction and reduce the chance of the incomplete combustion reaction. So here we want to define a parameter that we defined before. But before this, I think we have discussed this before in the beginning of the chapter, which is the limiting and excess reactant. So if I provide more oxygen than the stoichiometric amount, then of course the pentane would be the limiting reactant and oxygen would be the excess reactant. So this is what we are discussing here. So we have what we call the theoretical oxygen, which is the stoichiometric amount needed for a complete combustion reaction. Okay, the theoretical air, it's the amount of air containing the theoretical oxygen, which means that it's the theoretical oxygen and the plus the nitrogen that is accompanying it. For the excess air, it's the extra amount of air that is provided. So I don't just provide the theoretical amount, I provide the theoretical plus some extra amount, which is the excess air. And we have already seen this equation before, which is the percentage excess, and we said that the percentage excess before was the number of moles in the feed minus the number of moles. We called it the stoichiometric number of moles, if you remember. Now we call it the theoretical. Both are the same. So you want to call it stoichiometric, you want to call it theoretical, it's fine. So it's the number of moles in the feed minus the theoretical number of moles over the theoretical number of moles. We can rearrange the equation a little bit. So we can break this into 2 fractions. So it's the number of moles of air in the feed over the theoretical amount minus theoretical over theoretical, which is 1. And this is the percentage excess. Okay, and the excess number of moles is the excess multiplied by the number of moles in the feed. Okay, so this is the total excess as or the excess as number of moles. So if we calculate the percentage excess divided by 100 and add 1 to it, then we get multiplied by the number of moles of air, the theoretical, we get the total number of moles of air in the feed. So this is just a mathematical manipulation of the equation. It's nothing any strange here. So just to make this long story short, if we know the percentage excess, we can calculate the total number of moles of air in the feed, because we can find the theoretical amount from the balance of the equation by the knowledge of how many moles of the fuel, of course. So let's say for this example here we have 100 moles per hour of butane, which is C4H10, and 5,000 moles per hour of air are fed to a combustion reactor. We need to calculate the percent excess air. So in this case we have it, the givens are put in an opposite way. So we have already the number of moles of the air, and of course this 5,000 is the amount that is already fed. So this is the actual number of moles of air that we fed to the reactor. And now we want to find how much excess we have. So again, we just have one equation that we can use, and we just want to see what is missing in this equation. So the balance equation has to be written. This is the first thing that we have to start with. The pentane, this is the complete combustion, and there is an important point here, is that the theoretical amount of oxygen is calculated based on the complete combustion. So we assume that all the fuel is consumed in a complete combustion reaction. So we assume that the 100 moles per hour of butane are totally consumed in this reaction. So if we have 100 moles per hour of butane, then they will need 13 over 2 times 100. It's 1 to 13 over 2, so it's 13 over 2 multiplied by 100. So it's going to be from the stoichiometry of the reaction. So we'll need 6.5 moles per hour of oxygen theoretically. Okay, and we can calculate the theoretical air, which is the oxygen times 100 over 21, because we know that the ratio of oxygen in air is 21%, or the mole fraction, or mole percentage of oxygen in air is 21%. So we can calculate the total number of moles of air, which will be 95 moles per hour. This is the theoretical, and this is the actual. So the definition of the percentage excess is the actual minus theoretical over theoretical. So this will give us 61.6%. So here we calculated the excess based on the number of moles of air. So I have here the number of moles of air, and here the number of moles of air. Okay, this is the number of moles of air theoretically. This is the number of moles of air actually. We can solve the same example with oxygen, and you can do the same calculations, and instead of using the 3095, we can do the opposite. We can calculate the number of moles of oxygen here. We can multiply this by 21 over 100, and we are going to get the same output. And instead of having this with air, we can put the theoretical and actual values of oxygen instead of air. So anyway, so this is all what I want to discuss here, and this is all the basic things that we need to know about combustion reactions. And the next would be just solving a couple of examples, and we will be done with this chapter. So I'll see you next time, inshallah. Goodbye.